Well, welcome to the last two lectures of ASE 389, Learning for Dynamics and Controls, and it's been a true pleasure. You are actually the first cohort that is not my students, except for a couple of guys on this side. But last time we had this class, it was more of a pilot, and this time we took a lot of new directions, in particular to strengthen the theory, to introduce whole new sections on reinforcement learning, to introduce homework, and the last time we didn't have homework, and just revise everything to make it more effective. So we've seen topics regarding just basic statistics for engineers interested in machine learning. We saw Gaussian processes, perhaps that was one of the first structures that we saw how powerful they were for modeling dynamical systems. And then we saw the principles of regression and classification, just using simple structures. And then we move on towards exploring. Well, we spent quite a bit of time with reinforcement learning, and we saw the power that it has for solving systems with complex transition dynamics. We have homeworks. We played games with it, and we enjoyed it quite a bit. And then we move on more towards kind of the deep neural network structures, which we believe, and we've seen over and over, that they are becoming more and more powerful for the control of systems, of autonomous systems in particular, and in great part is because they can map large state spaces into policies, and with the weight of the use of lidars and cameras and even context sensing and inertial sensing as well, the state space explodes, and then it's very difficult to sort of use traditional techniques for finding policies. Therefore, techniques such as behavioral cloning, for instance, computational learning, reinforcement learning, they rely heavily on structures involving decoders, encoders, convnets, convolutional neural networks, and recursive neural networks as well. So we saw all of them. We saw how to perform classification and regression using DNNs, and as well as seeing coding as well with PyTorch and Google Colab, which have been a really advantageous tool for just teaching on the while here in class. So at the same time, you guys develop very interesting projects that I look forward to see. So they're in aerospace engineering, some of them more in robotics, some of them asking just basic questions on new structures in machine learning. And we're going to see today 2 presentations, and we'll have 3 more on Thursday, and then we have one of them that will be over video, that will be shared with all of you as we finish the class. So thank you all for being here.
Yeah, so we've covered RL in this class, and I'm not sure if we covered reputation learning, but it's basically just RL without rewards, without environment, and offline. So what that means is you're not learning any model, you're not trying to learn something that maximizes a reward function, you're not having a value grid. All you're doing is you're taking in some actions and some observations from something. Usually it's an expert because you want an actually good policy, and you'll map that. You're trying to learn what action to take given some new observations. So it's completely supervised. So you'll learn some policy, and actions are conditioned on the observations that you see. So most tests are unimodal, which means that there's only one good way to do it, when in reality, and that's a really simplifying assumption that a lot of model architectures make. Really, if you want to open a door, there's like 18 different ways to do it, not all legal. And the most simple, most basic example of this is just it's not this slide, it's the next slide. My bad. But here, it's the most basic example of this is if there's a fork in the road and both ways are legal to go to, then you want your model to take both ways. If you just use a unimodal model, it honestly might even consider any of the ways. So the behavior transformers does this. It tackles this problem of multimodal imitation learning, and the main advantages that behavior transformers bring to the table is that they don't assume that the time is purely Markovian. That's you only have, in the MDP, you're only conditioned on your last states. You can look at any window of time you want for transformers. You just need to specify.
What does it mean? BET is behavior transformers?
Yeah.
Okay.
Yeah. So, and because the architecture itself predicts stochastically which action to take, then you get this nice multimodal behavior. So I want to actually explain a little bit about the actual architecture of BET. So the first thing that comes in an imitation learning problem is your batch of continuous actions, given some observation. And a transformer, it does not like that. A transformer really wants discrete tokens. So you need some way to map that continuous action in your whatever 7-dimensional joint space or whatever to some discrete action, some discrete token you can use that represents some class of those actions. And they deal with k-means. So we just cluster the action space into some amount of clusters, and that's the discrete tokens. Each token is a bin center, right? Because it's like this bin 1, bin 2, bin 3. And it learns which of these tokens to take in sequence. So you can think of it as like a sequence of observations that actions come in, and it gets discretized, and then you run through the model. It's just a black box, and it comes out the other side, a sequence of tokens to take. But you're working with tokens. You need a continuous action. So the model actually also outputs the offset between the token and the continuous action that you actually took. And it learns that through 2 losses. The first loss is it's the focal loss. It's this focal loss. So this is choosing the actual bin to take from here, and this is the offset loss. So after you reconstruct the action, how far are you off from the real action that came in? And that's how this model works. There's a bunch of different ways you can actually do it for transformers. You can actually get away with like really naively discretizing, but it'll affect the performance pretty heavily.
I understand that. Yeah. You first cluster your action data set.
Yes.
So the action, this is not the state action data set, it's just the action data set.
It's just the action. It's just the action. Yeah. The state can come in continuously.
So you have some action data. Okay. Now so what is the second, the right side? What is it? What's the title?
Like this. This is the train. The train.
That's a train. Okay.
Yeah.
So you have observations sequence, okay?
So objects just come in. It's continuous. That's fine.
What does it mean individual?
Then GP is transformer. That's a.
Okay.
It's just a flavor transformer.
Okay. You apply that transformer, and then what do you get from there?
You get a sequence of these bins and their probabilities. So you sample from there. That's how you can get multiple different paths.
So you're finding the action sequence.
Yes.
Okay.
It's an action sequence.
Okay. And then what else? And then what happens? And you use that with your training, right? So you are.
Yeah.
So what's the reward function here?
So in the probabilities, you're just going to take the most likely one, and then
you have this mutational harmony, right? So that's reward function.
Yeah. It's the only reward function is like this observation sequence and
the ground truth.
The ground truth, like what action you actually took. But there's like 2 losses here. The first loss is like I just want to match the right bin, okay. And then the second loss is given the bin, I want to reconstruct the continuous action actually took to the ground truth, and that's the NFC loss.
There's no direction. Okay. Okay. Yeah. I see.
Yeah.
I mean, there should be an arrow going to the transformer, right?
Yeah.
Yeah. The cost function should be okay.
Yeah. So this is data flow, and then at first time, all you do is you get some observations in, and then the transformer it'll put something, you sample your bin for. I mean, usually it's obfuscating sequence. So you just take the last bin because it's a sequence of 5. Then your observation is currently bit 1. So you don't have actions.
So these sample actions, what do they mean? These like waypoints or
like these or
yeah, I mean at the end you have sample action, right?
oh sample oh yeah.
What are they? They're like
they're like
waypoints.
For the simulation, that they'll be like moving the end effector some distance relative to the object or something like that. It's just you're just working the action space. Yeah.
Okay.
Yeah. Okay. But you do get sequence of like actions. Yeah.
Okay.
Yeah, there's some things. Yeah, this is just more pictorially like you work with bin centers for those discrete tokens, and there's some offset between like the actual action and the bin center, and that's also talking about. That's how you reconstruct it back to continuous one. So if you have a new action like the smiley face guy, then the model at reference time needs to predict that not offset.
Okay.
Yeah. So my objective was at first this, it was to like generalize after going from BET. And at some point before Thanksgiving, I was implementing it in a simulation, right? That took way too long. That took way too long. I was like, so I just want to get it to work, but it actually works. So
cool.
it actually works. So I work in RoboMimic, and why RoboMimic? Because it's a framework developed by UT professor, or well, he was Stanford, now UT, and there's a bunch of baselines and standardized like data sets and standardized base like Zeek testing books. So there's three what is it, like tasks right now that you can use. It's the first one's lift, you just lift a block. Second one's can is pick and place can. You pick up the can and place it in the right bin. And the third one is more dexterous. You have to get a square nut and put over a square peg. And so yeah. So some baselines in the proficient human set, which is what I worked with. This is just like my best model I ever got. I get a success rate of 100%, 100%, and 55%, which is not better than
at what?
at like putting the square peg over the square peg, or like lifting the block up. That's like one success. That's like a success. So I did 100 rollouts after training, and it's 100% success rate.
The position of the plate.
Yeah, it's random. It's random. Yeah.
Okay.
Yeah. I have lots to show you at some points, but it actually doesn't do. It's surprised to me that it doesn't actually do better than the RNN. The RNN is the best by far on the square peg, and I have some hypotheses about this, but I can save it until the video.
What is the RNN here?
It's behavioral cloning with an RNN.
No, but which one about RNN?
BC RNN.
BCR.
And so 100%, 100%, and 84.
Okay.
Like
I see.
Yeah. And these are a bunch of other baselines. Yeah. So I didn't just do a single task. I didn't just train a single task. This is my extension. I was able to do this literally like yesterday and today. Yeah, I don't know. It's kind of amazing. I got this to work, but it actually works. So the core idea of multitask learning is instead of training on just one task, you're going to add some information in that specifies which task you're working on, and you'll train on all the tasks. So you're trying to hopefully learn some common representation that can generalize between all the tasks and maybe even boost performance. So there's actually positive transfer when I go from a hard task to an easy task. Like if I train 400 epochs on lift, right, on the lift task, just letting a block up, it's pretty simple. You can get 100% accuracy after maybe 150 epochs, 200 epochs. But if you train on a really hard task, like square, like putting square peg, you'll get 100% lift, 100% can out of the bat. Like I did 50 epochs, I did 100 epochs of square, then 50 epochs of can, 50 epochs of lift. It's like half the training time, and it does really well. But if you go from a really easy one like lift back down to square, you're going to have worse performance. But really, if you train more and you match the training time as a single task, it'll match train. It'll be like 55. Yeah. This is BET's like the original paper on the original implementation on their own simulation. So this is like a really complex task, right? You can see it's multimodal behavior here.
Is this your training?
This is inference. This is inference. Yeah. But these are like rollouts.
From your policy?
No, from their policy. From their policy. This is BAT how this is recorded, I think, 4 days ago, and this is on RoboMimic. It's really hard to get things working on RoboMimic. It is. I found it out, and like, it's literally doing nothing. Anyway.
4 days ago, not working.
Yeah, it's not working, but I was able to fix it, and these are shorts because I can't actually embed shorts inside Google Slides. Oh wait, sorry.
So you can do GIFs.
Yeah. So hyperparameters really matter. I'll just show some more failures just because. Actually, this is, yeah. So when the second is added distribution, it's pretty bad. And this is like if you have the offsets if you have like the offset reconstruction, if you put that loss too high, it'll be really bad also. Which is interesting because like it's one of their claims in their paper was like it's really robust to hyperparameter tuning. That's not true. So this is the model after I fixed like issues I was having earlier. It's 100% success rate in can and lift. These are all the good rollouts. So it does really well.
Okay.
Yeah.
You have a peg. You said like you have a square peg or something?
Yeah, I think it's one of these. Yeah, it's the hardest test. This is 50% accuracy, I think.
That's cool.
Yeah, so if you grabbed it wrong, it'll just be like, what am I doing? My end effector is
You don't need to implement that in a real world.
not difficult at all. Is it like, so yeah, at the very end, this is like some extensions. I can get to that whole one.
So he's using forces. Visual world know that does it know that it's touching the square power?
No, all it knows is all it knows is that, I think it can infer it because all it knows is the position like relative to the object. So it can infer it. Yeah. It knows its end effector relative to the object. It knows like rotation and a bunch of other things. Like I think it's a 19-dimensional observation space.
Okay.
And then this is some multitask. It's also multitask, but I don't have to go through it. It's the same thing essentially. If you train on the CAN and does really well in CAN, then it can do really well in Lift after a few epochs. So this is the multitask demonstration.
Why is it multitask? Because the same policy can do
Same policy.
the
Yeah.
cylinder or the square peg.
Yeah.
Oh, yeah.
Yeah. So they'll both have different observation
Yeah.
dimensions coming in. So I just pad it and I just throw one hot in there telling which task you're doing. Yeah, it's pretty cool. So some caveats about imitation learning in general and like behavior transformers that I'm working on. If you add distribution, you have this thing called covariate shift, which just means like your trajectory is slightly off, so it's going to accumulate error. You're not going to be able to get rid of this in imitation learning at all. It's not online, it's purely offline. So you're never going to get rid of it. It's just going to be there. And better architectures and better models is just a painkiller for it. It'll do slightly better in practice, which is often honestly good enough for a lot of surprising amount of tasks. Because this is like really the Achilles heel of imitation learning. If you're doing it offline, then you're going to either need a lot of data so you cover the entire like all stretches you'll ever see, or you have a really good model that does really good in practice. Yeah. So key takeaways: modeling is hard. It took me a really long time. Yeah. So gradient descent is taking models and tuning the hyperparameters until they work. I think I have my computer running for straight like 3 days, just tuning hyperparameters until I settled on hyperparameters that are actually good. And in the paper itself, it's like, oh yeah, this model is really robust to hyperparameters. Don't worry about it. You can throw anything in and it'll be fine. That's not true at all. And multitask transfer works. See some task transfer. So I think an idea earlier floated by was like goal conditioning and learning from play. So instead of just typing expert trajectories, yeah, the core intuition here is that if you just let a human out into a game or something like that, controlling the robot arm, the human will naturally do a bunch of things that make sense intuitively. They'll just play around with it, right? They explore the action space a lot, but they might not do what you want. So it might not be, so every trajectory might not be an expert trajectory, but a lot of trajectories can give you good information. So you just have all this random, essentially sequences that you get from a human playing. And what you really want to do is you want to be able to say, okay, given some set of observations, I'm going to input a goal, like essentially a goal observation, and I want you to be able to give me an action sequence that can get me to the goal. And that's all that is just a single concatenation of a single goal frame. That's all you do. And so like for this one, it's like, okay, I want my arm to be here. I want to these like slips. I want to slide the drawer. And then you want to sample some like plan and actually produce that from your models trained over this play. And traditionally it's done like with this encoder and decoder, and you're like minimizing some KL divergence, and you're making this, you're doing variational autoencoders. You can get this from a transformer just by literally, oh, this is a bit large, but all you literally do is you take BET and then you concatenate the goal, and then you just have a slightly different loss. It's just based on like, can you reach the goal state given some amount of time steps? So instead of like sampling an action, like sampling a new action every single time step, you'll pause your model and then actually roll out the action and see if you got the goal or not every maybe like 10 time steps, depending on like your sequence length. Yeah. So they actually did that. They actually implemented it. So I thought that was really cool. And they actually have it on a real robot, and actually beats a lot of benchmarks for multimodal real world imitation learning. Yeah.
All right, let's wrap this class up. Let's do it. Thank you all for coming. We're going to conclude our project on exploring molecular locomotion today. I'm Matt, this is Melissa, and let's jump right into it. Can we jump right into it? Can we? Okay, sure, let's jump right into it. All right, so a little bit of background. So we're interested in legged locomotion. The state of the art right now is kind of split into two camps, where we have, on one side, we have pretty much a pure end-to-end reinforcement learning approach, which is like blind, but like proprioceptive. So this robot like can't see what's going on, but it can feel where its legs are. It can kind of feel its way around, and that ends up being really robust to different environments. On the other side, we have more of a classical approach through nonlinear model predictive control, and this is looking at its environment. It is doing like planning and like a whole classical methods, or model predictive control. We're basically doing optimizing over a short time horizon. So there are pros and cons to both of these methods, and this is like very new last year or two kind of stuff. So advantages to this kind of pure RL approach is it's really good at like when there's like domain randomization, stuff that it didn't expect to see. So it actually learns this reflex where if it like kicks a step, it learns to like lift its foot up, and that makes it really robust. Additionally, even if it starts kind of randomly going onto a completely different surface, it's able to adapt to that and continue to be stable. On the other hand, because it is blind locomotion, so on this left side, these two are the same RL controller, and this is the moderative control. Basically, the NPC can like leverage its environment a lot more, and it's introspective enough we can see where it goes wrong when it does do things that are incorrect. Versus kind of RL, when it encounters environments it's never seen before, it doesn't necessarily know what to do about this. So kind of the idea was, how can we take these two things, there are pros and cons to both, they kind of can cover each other, and maybe see if there's a way we can combine them a little bit. So that was our initial project objective. That is a very ambitious project objective, and we were aware of that, because we're basically taking the state of the art and saying, this is the next step, let's do it. We learned a lot this semester. I don't think we improved by pure locomotion past the state of the art necessarily, but we were able to dive into both kind of the model-based area and the data-driven approaches and learn a lot. I think particularly something that was interesting was, so like looking at like these new RL tools like NVIDIA Isaac Gym, and particularly looking at some of the end-to-end reinforcement learning for quadrupeds, they can almost make it like look easy. Like the stuff that comes out of EQ Zurich is really impressive, and it's kind of like, hey, we just throw a quadruped in there and tell it to run. So we were able to download all of that software and like look at it and train a quadruped up, and basically we asked ourselves, okay, if we throw a biped in here, is it just going to magic bullet fix this problem, or is there a little bit more to it? It is significantly more tricky than that, as you would expect, but it was definitely kind of a good entry point, I think. All right, so we discussed this before in general. So we split the kind of into two camps as well. I looked into like learning augmented model predictive control, so how can we take trajectory optimization problems and leverage learning techniques to make them faster, and then Melissa looked into the pure reinforcement learning side. We both like helped each other out and kind of went back and forth between those, but in general that was like we'll have one person lead this, and that allowed us to kind of explore those two avenues. I do think that was good for like covering a lot of ground and learning a lot. I think in hindsight, like focusing more on one task might have helped us to like improve our results overall, but in general, I think we did a good job there. So I'm going to talk about the learning augmented NPC stuff, and then in the second half we'll go into the reinforcement learning with Melissa. So I went through a couple different iterations of this. My very first idea was essentially to take a complicated algorithm that runs offline. It's too complicated to run online, it doesn't run fast enough. And based on this paper that I read by David Servik at UC Zurich, basically the idea was take some trajectory optimization, run it a bunch of times in a bunch of different environments, and then train something to imitate it. And for an iterative process like that, it might take 50 iterations when you're doing it offline, but if you can start really close to the goal, it might only take one iteration. And so the idea was to basically learn to initialize it in order to speed it up. So about halfway through, I was working on getting set up for this, and I kind of realized this initial hypothesis is not, it's misguided. It's not wrong necessarily, but it wasn't doing what I wanted it to do, and so I kind of made a little bit of a pivot. And the reason is, when you're solving model predictive control problems, you're solving it on a receding time horizon. So you're basically stepping one little bit forward every time step. So you already have a really good initial guess of what your solution is going to be. So training a network to predict that initial guess, that's great for the very first instance, but otherwise it doesn't actually solve this like computation problem. It doesn't fix this problem where I want to take this thing, it takes forever to run and run it really quickly, because that problem would already be solved if you were running it as an NPC. So because my objective was to basically, improve the quality of that like online performance, I didn't see this as an avenue to success for that. So I reevaluated about halfway through. One thing that I think would be interesting is for a nonlinear problem, you'll have a lot of different local minima. In a high state space we don't know, but you can typically, there's multiple ways to do a problem. So something that is interesting is if you can like explore the state space offline, you can look at different local minima, you can start the same problem from a lot of different spots, and you can figure out like what the optimal solution would have been. And then if you train a model to predict that, now you have a way where maybe you were doing something and it's no longer the optimal move, but you're stuck in that local minima. Instead of using that previous horizon as your guess, if you had a network that was trained on the optimal guesses, you would essentially have an NPC that can kind of like account for local minima online. Now that is a tricky problem that at this point I thought was out of scope for continuing this, so I did do a little bit of a pivot. But I think that's the future of that kind of idea. So yeah, it is a valid thing, it's just not what I needed. All right, so on the other side, so I'm involved with the Human Centered Robotics Lab, and something we've worked on in the past is essentially, there's a lot of research groups with quadrupeds, there's not that many with bipeds. For quadrupeds, it's a pretty valid assumption to just have like a constant inertia. We call it like the potato model actually. Like when the robot's doing NPC online, it just has one inertia, it doesn't worry about the position of its legs, it simplifies things a lot. For a biped, that doesn't work because stability is a lot more important. You know, you're waving your arms around. I can't just pretend that this and this are the same thing, because they're not. But it's very tricky to take, you know, say your end effector positions and calculate what your inertia is. That specifically takes a very long time. So recent work in our lab has been basically training a multilayer perceptron to, like, you know, regress, you know, estimate that value. So given the end effectors as inputs, it spits out an inertia tensor. And that turns out to be really successful, like 95% plus accuracy, very good, and a lot faster, 134 times faster for the actual inertia values and 771 times faster for the Jacobian, which is what you would use in the training, and that will be very important momentarily. So with that in mind, we've made some analytical function where we can put in end effectors and get out inertia. We want to use that in an NPC, we want to use that in a trajectory optimization problem. So we would take that function, we put it in as a constraint. If you're familiar with constraint optimization, you really want the gradients of things that you put into it because you're going to do gradient descent. So the kind of crucial thing that happened with this was they took this network and they wanted to get the gradient, so they used Casati, and basically, which is an analytical differentiation software, and so it like takes this function and symbolically figures out what the derivative is. The problem here is PyTorch, whatever you train your network on, knows that this is a neural network, and it knows that it's solving the same problem over and over and over and over again, so you'll parallelize it, make it train a lot faster. Casati does not know that. It will take an arbitrary function and give you the derivative. So when we did this, we being the previous researchers, I wasn't involved with this, using Casati for that symbolic differentiation, you lose that parallelization. So now, instead of having that really nice, you know, evaluating all this in the GPU, you're trying to get the derivative of this neural network, which is huge, you're doing it like one operation at a time. And that is really problematic. So that was my theory going into this. I learned from the first time that I want to confirm a theory before I jump into it. So I actually basically took this program and I profiled it using like a C++ profiler, and that'll go through and tell you, you know, how many times this function is called and what percentage of the time it spends in this. We're not going to go through this GIF, which is it's sliding a little bit too fast to read anyway, but this is actually the full like call stack of everything that happens in this trajectory optimization. And what I found out was this thing takes about 28 seconds to run, and almost all of this time is spent evaluating the Jacobian. So I was right. Cool. Inequality constraint Jacobian, 18 seconds. So really all you need to do is take that network and use PyTorch or whatever to get the gradient that you're already doing to train it and plug it into your optimization and interface those two software things together. And this will speed up by 20 seconds real fast. At this point, it was getting late in the semester, and this is already strayed off from being a learning project towards like almost a software project. I wouldn't have, if I had continued this part, I wouldn't have even like trained the network myself. It was already trained. It would just be an implementation thing. So although my research is going great with this, I decided to work with Melissa a little bit more and focus on the reinforcement learning aspect so that I can make sure like as a class project and as like a learning exercise, I got a sufficient amount out of it. That is the conclusion of the NPC side. And we can ask questions later, but otherwise, I'm going to go into RL. Take it away.
Okay. So I'm sure you're familiar based off of our past presentations in this class, but we use NVIDIA's Isaac Gym, and you can see it's training animals to walk with various linear velocity commands. It's really good for training quadrupeds. It leverages the GPUs for training and with massive parallelization. So yeah, these robots are moving with random 2D based velocities that change over 10-second intervals, so they're really good at that. So Lego Gym also has a bunch of tools that can be used to make your policies more robust. You can randomize the friction of the surface that they're walking on. You can randomize added masses to the robot's base. You can randomize simulated impulses to the robot base. You can add noise to your sensors. You can start with different initial positions and velocities. Another thing that was really useful, especially for developing policies for the bipedal robots, was specifying links that result in termination. So when a certain link touches the ground, it terminates. But if it doesn't terminate based off of that, then it just times out based off of your max episode length.
Okay, this is my slide. All right. So before we get into the rest of the RL and the results, Basically, the underlying network architecture that was there for Light Engine is what I want to talk about. And again, we didn't make this stuff from scratch. We basically took a pretty complicated repository and tried to, that is state of the art, and tried to get a grasp on it as two newcomers to the field of learning. So this is the default architecture that's in there. And essentially, it's an actor-critic architecture, so we have two pretty regular multilayer perceptrons. The actor network looks like this, where we have a bunch of different inputs. We have the base velocity measurement, we have a gravity vector, velocity command, joint errors and joint velocities, the last motor commands, and then a small height map around the robot. So these are all things that kind of map to real sensor data, stuff like a depth camera, an IMU, and that's what's coming out of the simulation. So that goes into this pretty deep network. We have 3 hidden layers, and it spits out 30 inputs, or 30 outputs, excuse me, that are the actuator commands. So that's like what you'd be used to, like, okay, this network takes in sensor data and spits out outputs, and spits out motor commands. That makes sense. The thing that was interesting that I learned about was the critic network, which they add in there as well. And what the critic network does is the architecture is identical up to this last part, and the output is one single output. And it's trying to estimate the value function and basically learn the Q values during the training process. And to my understanding, the way that helps is essentially we have this separate network that's watching the actor as it's training and trying to predict what the reward's going to be. And so when we go to update the policy, the critic has an idea of how can we improve this policy. So we can use the critic to kind of guide how the actor updates this policy, and it ends up causing the whole thing to learn a lot quicker. So this, we'll talk about some of the repercussions of this later, but this is how it is working right now. It's just a regular feed-forward, kind of vanilla development work.
So these are our overall results. You can see that we started from a very poor place with the initial policy. Atlas shouldn't be launching itself like that, so we were very suspicious on the contact physics in Isaac Gem. But you can see the final policy, it can stand.
That's very funky.
Yeah, we realized that really fast. And yeah, so it walks, it kind of shambles.
That's what we told it to do, just to not follow.
Amazing work.
Yeah. Yeah. So this is just sample data from one robot from the pelvis joint. In the initial policy graphs, you can see that this base velocity has an error of 3 meters per second, but for our final policy, we have an error of the maximum of 0.4 meters per second. You can also see that our joint positions and joint velocities, base velocity in the z direction, everything is a lot more stable than the initial policy. So marginally better. So yeah, to deal with the interesting contact physics, we reduced a lot of the collisions on Atlas to reduce any potential for strange collisions. So yeah, this helped a lot. We also removed self-collisions, and it seemed to perform a lot better. So a lot of the work went into tuning the rewards. These are the major rewards that we spent a lot of time working with, obviously tracking your linear velocity commands. Like a gym has a reward for long steps. So based off of your first contact on a foot, if you keep your foot in the air for a longer amount of time, you get more of a reward. You get a reward for keeping the orientation of your base with respect to your planar surface parallel, and if you maintain a specified base height. Obviously, this works really well for quadrupeds, but this is a biped that can't use point feet to walk all that well. So we had to make custom rewards. If your center of mass is above the knees, you got rewards. If your forces were distributed across your feet, you also got rewards. And you can see the consequence of not having a good distribution of weight across your feet. Atlas decided to walk by putting most of its weight on one foot and kind of kicking off on the other foot.
So this is not the final, this is an then the next are intermediate policies.
And you can see the collisions, the collision boxes as well.
It's very good for zombie movies.
Yeah, that's yeah. So these are some more performance tuning parameters. We penalized termination of a lot of the joints. We realized that if you don't specify termination on a lot of the upper limbs, it learns to crawl. That's not really helpful for walking.
We lost that GIF, but it learned to crawl, which was very fun. When we woke up to that, and it was crawling around the floor.
Also.
Yeah, I don't really. Yeah, we also realized that when you're standing and walking, you don't have joint positions that are the maximum all the time. So we also included the self-penalization of joint positions. We also included a penalization of feet contact forces above 5,000 newtons. If you Google it, Atlas weighs 90 kilograms. So 90 times 10 is what is that?
900.
Yeah, 900. Yeah, and then we implemented these two curriculums. Like a gym comes with the linear velocity curriculum, where if your robot is able to walk at a certain velocity range where you get 80% of your tracking rewards. It increases the range so that it makes the robot walk faster. Atlas never really achieved 80%, so we never really saw any effects of that. We also implemented our own reward of decreasing the feet size. So feet are a really important thing for bipeds. Quadrupeds can walk with point feet pretty well, but bipeds cannot. So we implemented that curriculum. And then this is the result of implementing that. You can see that it is standing with the true foot size of Atlas, but not very well. Yeah. Anyway, yeah, these are conclusions.
We love transitions. All right, so what did we learn? Bipedal locomotion is very hard. I know that might have been obvious, but it's very difficult. We opened IZGym on the first day. Within 10 minutes, we had a quadruped walking around. And that's because that was some of the base examples, but just like in general, I don't think that carries over super easily like we might have wanted it to. So very tricky. And there was a lot of stuff we learned, and there were a lot more interesting intermediate policies that we did not record, unfortunately. But yeah, it was a very interesting experiment for sure. So one thing I think that was particularly interesting, especially from looking at some of the literature that's come out more recently, is that I think time varying processes really need to look at like a temporal architecture. So the most successful quadrupedal walking comes from something that like understands the idea of like time pretty much, particularly like it's called a TCN, a temporal convolutional network, where you're basically sliding a network over like the last 2 seconds of like your proprioceptive history. And that is where that kind of like reflex to kick the stair and then go over it appears from. And so I think the quadrupeds will work with just an MLP, but the performance is massively increased if you're able to incorporate the temporal aspect. I think for a problem that's harder, like a biped, just having like a vanilla MLP just is not going to work. You need a better model. You need something that understands like that things happen over time. So that would be probably the first thing to explore is different architectures. IZGym takes a ton of computing power. Even on like a lab research computer with a really good GPU, we were struggling sometimes. Like if the numbers were if the number of simulations was too high, it would just crash. So that still remains a barrier of entry, I think, to this kind of area. But it's certainly interesting. And if you do have a lot of processing power, it's a very powerful thing to use.
All right. So I learned that reward tuning is very difficult. It ate up most of, I think, all of my time. You can see an example that reward tuning is like an interesting dance between you and your robot. I told it to distribute weight amongst its 2 feet while walking, and it decided to hop, and that was not really what I wanted. So really, it's a lot of focusing on like making rewards to tell your robot what you want and not how to do it. So I learned a lot about that. And that curriculum was really important, and it was the thing that got Atlas to stand and walk in the end. So this is just a little bit of future work. If we were to increase the robustness, we would use a lot of the tools that like a gym has, which is what I mentioned before, random pushes. We didn't see it here, but they have a terrain curriculum where they spawn animal in different terrains like stairs and rough surfaces. So that would also be something we could do. Again, this is just adding noise to the sensor states or the sensor readings, randomizing surface friction and added mass. And
yeah, I think we already discussed the different architectures. So the TCN is an obvious step. And another thing that's really important was, so even in that actor critic kind of workflow, one thing that saw a lot of success as well is giving the critic like privileged information. So ground truth basically from the simulator, stuff that it's not supposed to know. And what happens when you have that kind of like teacher learner thing is your learner network is able to kind of like implicitly build a model of state estimation because it's imitating something that knows what's happening. And so it's able to figure out what it needs to do without that information. And then when it gets out in the wild, in the real world, it doesn't have it, but it's learned a really nice estimation that's like robust. So that's something also interesting. Due to time constraint, like I think if we had done this for like pure research purposes instead of a class project, we probably would have spent a lot more time really looking at the collision physics and like really looking at the footsteps and stuff. We were able to train stuff that was robust to that, but I do think like there's a decent chance that that could be something that held us back. Is just that like having a lot of little pointy edges and stuff just makes it complicated, especially if it's not like realistic to what actually happens. Yeah, these are references. Thank you guys so much.
The title of our project is Aerodynamic Sensing for Hypersonics via Machine Learning. Okay, so to start, we can talk about the hypersonic flight environment. So the extreme aerothermal environment that we experience during hypersonic flight really limits the availability of measurements that we can take on board the vehicle. So we can't really have pressure sensors installed external to the vehicle. We don't have as accurate information about the aerodynamic state. So we really want more information about aerodynamic loads, specifically distributed surface pressure loads for GNC purposes so that we can get the coefficients of lift and drag and moment and be able to use those in our control algorithms. So to solve this problem, we have sort of a novel strategy called FAST, which stands for Full Airframe Sensing Technology. So the idea here is that the aerodynamic loads are encoded in the structural response of the vehicle. So we can think of this as using the entire vehicle as the sensor. And to do this, we can pose an inverse problem to infer aerodynamic pressure loads from measurements of structural deformation. So in our case, measurements of strain. But generally, inverse problems are really computationally expensive to solve, and we want to be able to do this in real time for a control system. So we're going to accelerate the inverse mapping using machine learning. So to highlight the vehicle as a sensor approach, so first in the offline phase, we develop an aerostructural forward model, and then we use that forward model to generate training data over a large range of flight conditions or parameters. And then we use our machine learning tools to generate an inverse map. So that's all done offline. So then once that inverse map is learned, then we can move it online, and we can obtain a strain measurement from our onboard sensors, use the learned inverse map to rapidly identify the quantities of interest, and then we can estimate or reconstruct the pressure field, which is ultimately what we're after. So to highlight the three different sort of methods that we're going to be presenting today. So the inputs to all three are our noisy sensor measurements. And then the mapping from those noisy sensor measurements are decision trees, which has been done in previous work. And in this project, we're building further on that using neural networks, both standard and Bayesian neural networks, as well as Gaussian processes. And then the outputs from all of those are going to be a prediction of pressure quantities of interest from our machine learning regression model, depending on which model we were using. So the outline for the rest of the talk, so first we'll talk about the generation of the training data, then we'll talk about the POD, proper orthogonal decomposition representation of the pressure, so that's representing the pressure in a low-dimensional space, and then training our machine learning models, so the Gaussian processes, the standard neural network and the Bayesian neural network, and then we will compare the methods and conclude. So the vehicle that we're considering for this study is the initial concept 3X or IC3X hypersonic vehicle. So for our CFD analysis to compute the aerodynamic pressure loads for training, we're using the CART3D tool. So we run the CART3D tool over a range of parameters, so Mach numbers and angles of attack that you see on the slide. So we get a total of 44 different parameter combinations. And so for each of those parameter combinations, we get an aerodynamic pressure snapshot. And then for each of those snapshots, we can use our structural model, so our ANSYS structural model, to compute a corresponding strain field for each of those parameter combinations. And then to actually generate additional training data to represent kind of synthetic noisy data, we can add realizations of noise from just a standard white Gaussian noise model.
So the ANSYS simulation, it's a dynamic simulation?
It's a static structural simulation.
It's a static, so it applies arbitrary forces, or what?
The loads that are computed from the CART3D tool. The CFD.
So these are the expected loads during flight?
Yes. So that's why we kind of run over a range of Mach numbers and angles of attack, so that we can get sort of snapshots of potential aerodynamic loads that we'll see. And the sensing strategy that we're trying to do is kind of taking everything instantaneously, so we only need kind of like the instantaneous picture of the loads and the corresponding structural response.
And those loads are at discrete point, or how, or is, are they at the pressure load, like distributed pressure loads, or?
Yeah, it's a distributed pressure load. So it's, yeah, so you can, this is actually the full volume field, but you'll see a few pictures showing like the pressure on the surface of the vehicle.
Okay, thanks.
Yeah. Okay, and then just a little bit more detail about the actual training data process. So first, computing the snapshots. So we have our input parameters, and then we have our aerostructural model, which we feed the parameters into, and then we get a sensor strain response at all of our sensor locations. So we do that for each of our input parameter combinations. And then for each of those snapshots, we can then add Gaussian noise. So we're choosing 200 samples of Gaussian noise samples for each of those snapshots. And we choose the noise level to be the standard deviation of the Gaussian noise to be 1.67% of the maximum strain response over all of the snapshots. So that is a pretty pessimistic view of what the noise level actually would be. So we're actually kind of increasing the noise level to kind of push our machine learning models to see how well they can do. So once all of that is done, we can assemble everything into a data matrix, and that's actually what we give to our machine learning models for training.
So this reduced representation of the pressure field is kind of where the magic happens, if you will, or it's one of the places where we're able to save a lot of computation time. So that's through the process of proper orthogonal decomposition. This is just one of those phrases that also goes by a lot of different names. So another popular thing, it's kind of analogous, is singular value decomposition.
So really what happens here, if you recall from like a linear systems class or something of that nature, your professor will usually tell you that that sigma term and your SVD, the singular values are usually organized from, I believe, highest to lowest. And so when you do that process, your V matrix likewise needs to be reorganized. And so what we're doing is, in order to achieve this reduced order model, we're looking at the number of modes or number of columns that essentially give us the maximum amount of energy possible. And so for this specific problem, we've come to the notion that about 5 modes is kind of where we're going to see the most amount of energy we can get, or we're going to get marginal improvements as we continue to increase the size of our model. And so taking that and then taking out that Q bar term, which you can just think of as like a bias that we take out so we don't have any scale factor issues, we're then able to reconstruct our pressure field via the equation that you see at the bottom of the screen.
So where are the singular values here? Or the V, is V the singular vectors?
Yes.
Yes.
Okay, okay. And Q is the bias.
Yes,
Okay.
and so then you'll see also later, so we have 5 modes, and so because of that, that's why we have 5 pressure coefficients.
Okay.
And that's the goal of all of our different models, is to try and calculate those 5 different pressure
Okay,
coefficients.
all right,
Yeah, the CK is in that equation there.
okay, okay.
So speaking of those pressure coefficients, like I said, I said there were 5. This is a picture depicting kind of the representation for 3 of what those pressure coefficients could look like. Keep in mind that the pressure scale, that's dimensionless units because it is a coefficient. And then it's also used on a log scale, kind of just to make things a little more even across each one of the coefficients that you see.
So what is negative pressure?
So this is a little bit misleading. So these are pressure modes. So
Okay.
when we compute, so when we center the snapshot matrix, so that bias there, we're going to subtract that from all of our snapshots. So that creates some negative values there. So when we compute the SVD, like these are the modes we get. So it's dimensionless. So it's not really negative pressure. It's just the way.
These are the vectors? This is the vector?
Yes, these are the modes.
Okay, I see.
And so moving on, I guess, to the first process that we used, I was seeing how we could use a multivariate Gaussian process to try to directly calculate the pressure coefficients. So if you recall last time, I was trying to use a Gaussian process to predict the Mach number and the angle of attack. However, that also had an extra step to it, which would be that you need to interpolate via a lookup table. And so I said, well, why not just try to completely work around that and just directly predict the pressure coefficients. So you can kind of see the outline. So I have all 44 of our strain gauge measurements for a given run that will then be prepared. They'll be used, some number of those rows will then be used to condition a Gaussian process, which is trained. From there, I then sample the posterior to get our pressure coefficients. I then reconstruct the pressure field, and then I can compare to a set of testing or truth data that I've set aside. And so the tools that I was using for this was a combination of sklearn, TensorFlow, and SciPy. So another thing I had to do was I had to kind of look at what kernels I want to test, and so I ended up selecting 3. All 3 of these are anisotropic or stationary kernels. I guess the abbreviated summary of what those are. They're just kernels that support using vector or multidimensional inputs versus a scalar input. So I have a squared, exponential, and exponential kernel, and then a rotational quadratic kernel. And then these are kind of just examples of, if you were going to take the scalar case, here's what their distance distributions look like. And so now for the results. So this is another thing that I was able to improve on from previous work. So as Dr. Sentis had mentioned, usually a really big issue is that once you get to larger dimensional matrices and having to try to invert them with a Gaussian process, you're going to get matrices that are nearly singular or that are singular. However, if you do something like a least squares approximation approach to solving this, you're able to get around that. This does incur a slight runtime penalty, but I was saying, for the sake of getting more accurate information, that would be something that would be worthwhile. So I was able to end up conditioning on 500 rows, like I said, all 44 strain gauges per row, and then my posterior test points I tested on 2,000 rows of data. And so as you can see, for all 3 of these, by the way, this is the L2 error, slight mistyping on my axes. But the median error for all these were under 3%, irrespective of what kernel I used. However, there were some outlier points, which would reach up to 15% error. There's a couple reasons that I feel that could be occurring. But I think one of the biggest ones is because I'm randomly sampling what rows from this data set I'm using. If I were to kind of take an approach of something like finding a way to model the data set as a Latin hypercube, or even doing something like a design of experiments where I could guarantee the data that I'm randomly sampling is actually representative of the full space that this data set can encapsulate, I feel like then I could eliminate a lot of those outliers, but that was just something I didn't have time to get around to. So overall, I think that these were pretty good results for the Gaussian process. And then these plots, I guess to kind of reiterate, this is taking the pressure coefficients, doing that reconstruction step that we showed a couple slides ago, and then it would do the same thing with pulling aside just like a testing data set, and then that would be like our truth versus what our predicted was.
So the strain gauges, ANSYS simulates what the readings of a strain gauge would be?
Yeah.
Okay.
All right, and come to the middle, so it wouldn't cost. All right, so then the last sort of set of techniques that we wanted to look at was neural networks. And we've sort of been updating on this part throughout the semester, but we wanted to implement both a standard neural network and then also a Bayesian neural network and see how those methods compared to some of these more traditional or like slightly more interpretable methods that Julie and CJ have been talking about. So for the standard method, what we want to do is have it predict those pressure POV coefficients directly, just like CJ was just talking about with the Gaussian processes. So we'll set up our very traditional neural network, predict those 5 CK values, and then reconstruct our pressure field. Slightly differently for the Bayesian neural network, what we do instead is we want to impose probabilistic predictions with some sort of quantification of the uncertainty involved. And there's a couple of different implementations that people use to do this. One way that they do it is that you assign a distribution to each of the weights in your neural network rather than just a scalar value. And so this is sort of accounting for that uncertainty within the structure of the neural network itself. And then the other way that the uncertainty gets added into the system is you also can account for it by adding the variances, the covariances, as additional outputs that your network is predicting. So rather than just predicting, it's C1 through C5 for the coefficients, you predict those 5 values, and then you also predict all of the entries of the covariance matrix so that you have the full Gaussian characterization of your outputs.
So you do the two things in one. You do both the prediction of the covariance and the weights being distributions themselves.
So what you'll soon hear is that we had some trouble getting some of the.
Just move it around. Okay.
We had some trouble with some of the implementation details, so I'll talk in a slide or two about what we actually ended up implementing.
Okay.
But this is like the general idea of, in a perfect case, what you get from the Bayesian neural network. So first of all, for the standard neural network results, you can see the same type of plot on the top here of that L2 error of the pressure field. And so we can see again that our error is below 2%. So that's as good or maybe slightly better than the other methods that we've looked at so far. And you can see that there are also quite a few outliers in this method, probably even more than in the Gaussian process. So now we're starting to see some of these trade-offs that we get between different methods where maybe the Gaussian process has slightly fewer outliers, but it's less accurate. And so you have to decide, as the person implementing your...
What was the error in the Gaussian process, the mean?
Only slightly higher, like
only slightly higher?
I think.
Okay.
Yeah, so that's sort of the trade-off we're looking at. And so what we want to do is get those coefficients, reconstruct our pressure field, get the error here. And then these plots on the bottom are breaking down those errors into a little more granularity by looking at the distribution of each of the coefficients individually. And so you can see it's a similar type of characterization. And within individual coefficients, we can see that there's outliers up to like 15% error. And that makes sense because what we're doing is when we do that reconstruction, it's sort of an averaging technique. Or an aggregation, and so some of those inconsistencies get washed out when we reconstruct the system. The Bayesian neural network, on the other hand, we were able to get an implementation that has probabilistic weights, but still deterministic outputs. So the distinction here is that using those probabilistic weights, you're accounting for the distribution of each of the weights in the network. But what we weren't able to get implemented efficiently enough to present anything about was characterizing that covariance matrix as part of the output. And that's just something that we'll talk about in the trade-offs a little bit more, but just note that that's a difference between the ideal case I just presented.
So is it possible that the outliers, it looks like they are, the value of the outliers is less, because the other one was going to probably point.
So the
maybe
thing
I'm
to
wrong.
note is that this is
is it 20
magnitude higher.
It was 0.02.
And so
I see.
yeah,
I see.
and so that's the interesting thing is that our implementation is nowhere near as accurate as the deterministic one was.
Yeah.
And one of the questions that, again, I'll mention in another slide or two is you have a question of how much data do you need for different techniques to be able to train them effectively as a trade-off with the dimensionality of your system. So I'll talk about that a little more in the slide or two as well.
Okay.
But just note that the predictions are definitely much less accurate than
Yeah,
the network.
yeah.
At least in the implementation that we've been using.
And in TensorFlow, and I'm not a user of TensorFlow, but is straightforward to implement a Bayesian neural network? Is it more elaborate than implementing kind of a standard neural network?
It's definitely more elaborate.
Yeah.
Okay.
Yeah, the layers and the structuring and the sizing is just a lot more complicated.
Okay.
You have more choices for what your layers are going to look like.
Yeah.
I think it also requires.
When you initialize the weights, you have to initialize the mean and the variance itself. So they're probably sensitive to that as
Very
well.
sensitive to the parameters too.
Yeah.
So we just couldn't. I mean, that was the best parameter combination that we could get, and it still wasn't very good. And I'm sure there's other things that we didn't try to make it better, but it just wasn't doing very well.
And I mean, one other notable thing, a big reason why we weren't able to get the other portion of the uncertainty incorporated into the Bayesian network is that it requires changing your loss function to not being an MSE anymore, but rather being your negative log likelihood.
Yeah, yeah.
And for some reason, that is just like a much more difficult thing to get the system to run accurate. Like we couldn't get it to work with that implementation.
Okay.
And people have gotten it to work, so it definitely is possible. But it just shows that neural networks. I never used neural networks until this class, and I was able to get it working. So that's kind of the trade-off.
I would also say too, like as the number of hyperparameters that we were trying to tune continued to increase, it kind of got to the point where it's like, I don't know how many of you are like tuned like GADI controllers or something like that, where it's like you get to that point where it's like I have to do a line search now to properly find what my parameters need to be, and like that's not necessarily a simple trivial process. That's something that can take days. It's something that, depending on how big the data set is, can take weeks.
Yeah.
It kind of started snowballing into a problem of like us wanting to show the best results we could in the time that we have.
Okay. Yeah, so just revisiting the optimal regression trees, which I sort of presented initially, and it's all from previous work, so I won't talk too much in detail about the details about the training process, but just as a recap, they're essentially a decision tree that takes in the same inputs of the noisy sensor measurements and outputs the PUD coefficients, so we train a decision tree for each of those coefficients that we're trying to identify. And the benefit here is that they're really interpretable, so you can kind of look at the tree, know exactly what's going on, and understand it from an engineering perspective. So we just wanted to show the results from the optimal regression trees. So the reconstruction L2 error that we've been showing the same sort of plot here on the right, that is the L2 error of the pressure reconstruction. So we're going to compare all the methods in a minute.
Okay.
All right, so this is a stack up of, you've seen all of these plots before, so this is just the L2 error for each of the different implementations. And so note that the three on the left side, the GP, the standard neural network, and the decision trees, they all have the same scaling. And then as we talked about, the BayesNet is a different scaling. And so a couple of interesting things to note here are that, first of all, a little bit surprisingly to us, all three of those more traditional techniques on the left have pretty similar error, or median error at least, and pretty minimal outliers as well. And so we definitely weren't expecting the GP actually to perform as well as it does, given the higher dimensionality of our problem. And another thing to note is that in addition to the difference of the Bayesian neural network being a much poorer predictor, it's also really interesting to note that the decision trees have almost no outliers. And by comparison, the GP and the neural network both have a lot of outliers. And so, it just goes to show you some of the differences.
Yeah, it's kind of going back to square one, right? What you discover here is that, at least for the parameters that you chose, there is no advantages of using neural networks with respect to decision trees that you already were using.
Well,
right? I mean, decision trees is something that you had from before, right?
Yes.
And then what you're showing here is that the mean error is similar,
Yes.
but a bit worse than standard neural networks. But then the price to pay is that the outliers are much higher on standard neural network, right? So would that tell you that it's better to stick to decision trees?
Yeah, especially with the lack of outliers and sort of with the robustness that we see with like less outlier predictions in combination with like the interpretability of the method and being able to look at it and see its logic, it just makes a lot of sense to use regression trees, especially for this problem that we've
Okay, sounds great.
So one other thing to talk about is some cost trade-offs for the timing. So one thing to note is that all of these methods require the storage of those POD modes and the reconstruction from those mode shapes. And so that part is baked into the sort of the assumptions of our comparison. So you can't get around that with any of the methods. And since we haven't implemented these on a flight computer, we don't have hard times to compare. But we expect that all of these methods would evaluate pretty quickly. That's sort of the point of all these different ML techniques in general. But one thing that's a little different is the neural network has a lot more parameters to store than any of the other methods. And that's one reason that those outliers might be more extreme, is that you're fitting one function that's supposed to predict everything, whereas Julie and I were talking about this earlier, and a decision tree, it's making much more robust separations and then fitting locally with its further decisions as you go down these branches. And so that's sort of a trade-off you have. And then with the GPs, they're sort of a funky case because they're the only one of the methods we looked at where if you get more measurements, you actually might run into more problems because it can't handle getting too many things fed into it at once. And that's it's good that it was able to compete pretty well error metric wise, but it's not ideal to have a method where you get penalized severely for having more and more data.
Okay.
And then in terms of training, the Bayes network, as we mentioned, was very difficult to train. The GPs were really quick, and then the neural networks and regression trees took a little bit longer. So we completed our Gantt chart and followed all the different methods, mostly being able to compare all of the error metrics at the end. So that is satisfying. And then here are a couple of references. And take any questions. Thanks for listening.
Good evening, guys. So today we're going to be talking about, as we've been discussing in our project updates, the optimal control using RL and optimal control strategies for high-speed UAV, for optimizing high-speed UAV trajectories. So this is our basic layout. So our problem statement is basically to combine a model-based optimization approach with a reinforcement learning approach, and then use the solution for the model-based learning to get a better convergence for RLs. And we'll be training the policy using rollouts, which basically means for each state there's another full simulation you do. So we'll be doing multiple rollouts, and as you can see, this process kind of gets very computationally heavy. And so another thing we wanted to do is assess the computational costs of training and maybe formulate some abstractions or simplify the state space a little bit to so that the problem is more easy to solve. Space. I think you have to click back on the presentation. So our quadcopter's dynamics are modeled as follows. So this is the 6 DOF case, a 6 degree of freedom case. But for our purposes, we're only including dynamics in the translational directions. So this is essentially just a simplified version of this. And how this is related to RL, that's on the next slide. So our RL model, our state is a 6-dimensional vector with position and velocity, and then our actions is a tuple with thrusts from each of the quadcopter's blades. And our reward function is very, very simple. As we've discussed previously, it's just for the states that are not that are anywhere other than the gate structure or within the gate, or actually, okay, back up a little bit. This, if for any state, there's a minus delta t that's going to be associated with that state, and if the state passes through a gate, there's a positive 5 reward, and if it collides with the gate, it's a negative 5 reward. And ultimately, how the thrusts are mapped are through a neural network created by DDG, which can be basically obtained by training the model through a software called DDGP. And so we'll talk about that a little bit more on the next slides.
So as my partner was saying, we are trying to combine model-based control with reinforcement learning. The model-based approach is using the Hamilton-Jacobi-Bellman equation. This can give us, based on the value function of the problem statement, which was based on the dynamics of the drone with 6 dimensions. That is the Hamilton-Jacobi-Bellman equation, and we have to solve this partial differential equation on the value function. And that +1 that we see there is because the cost function of the optimal control problem is just 1, which means we are trying to solve the problem as fast as possible. So this can be seen as a time to reach problem. And we are outlining here the advantages of the model-based approach, which is we can solve numerically the partial differential equation to obtain the optimal control offline. And then we can find the feedback policy, and this can be applied online with minimal computational effort. But the disadvantages are that the solutions are only feasible on a small portion of the state space, and also this depends on the course of dimensionality, which means the solution is intractable for more than 6 dimensions, which is why we're using this, and then reinforcement learning using the full dimensions of the drone, which are 12 dimensions. And yeah, the quadrant dynamics are often 12-dimensional, so we cannot solve the problem only using this. Then with reinforcement learning, the good thing is that no explicit model is required, and we can find the policy through simulation and rollouts and trying to converge to the optimal policy. But this also suffers from poor sample complexity. Sometimes it can never converge to the optimal solution, and we require a large number of rollouts. So combining with model-based control, we can make the algorithm to converge, because if we don't have a good initialization of the policy, then to explore all the state space is very hard computationally. So that's why combining these two methods is a
So
good.
you have 200 dimensional state.
Sorry.
You said you have 200 dimensions.
Yeah, with reinforcement learning, it's like we have to explore a lot of state spaces. The state space is very large because we have 12 dimensions of the drum.
12 dimensions.
Yeah. Considering the position, velocity, angular rates, we can get to 12 dimensions. So that's why sometimes the algorithm never converges. Okay, so what we were working on then, the first part is making the solver for the Hamilton-Jacobi-Bellman equation. For this, there's a toolbox available online. This toolbox is based on MATLAB. There's also another toolbox on Python for solving Hamilton-Jacobi-Bellman equations. We solved the problem with 6 dimensions. Unfortunately, 6 dimensions, we cannot see that, but in this image, I'm showing the solution of imagine the problem only for 2 dimensions. We can see it here. So all these curves we are seeing are the time to get to the origin of a simplified problem of two dimensions. So that's just to see that the algorithm works. Unfortunately, with 6 dimensions, we just have a multi-dimensional array and we cannot visualize that. But yeah, we can solve this in MATLAB using for the 6 dimensions. Then we have to download this policy as a .mat file, and then we can upload that into Python, which is where the code is based for the reinforcement learning part. Okay, so now getting to reinforcement learning, we use policy gradient to learn the Q function and find a policy. From the Hamilton-Jacobi-Bellman equation, we generate a Q function it's a multidimensional array on 6 dimensional states, which is paired with the controls. The controls are going to be 3, like the thrust inputs in the 3 directions. So yeah, that's the Q table. And then we can find the optimal policy by taking the value that minimizes that, which can be seen in this equation. And for many dimensions, this algorithm may never finish, or it can yield to unrecoverable states. That's why the policy obtained from the GB equation can serve as an initial good policy.
Yeah, so the way we actually went about running this was in a simulator called Gym PyBullet Drones. So pretty much what this is an OpenAI gym environment, and it's based on this physics engine called PyBullet. So it allows everything to be just run in Python, which is pretty nice. A lot of well-known drone simulators like AirSim are in C++. And so for us, we felt it'd be easier to use this specific environment. What was also nice about this environment is that they're kind of like baseline virtual environments that we can customize, that we can build custom environments off of, as well as incorporations of well-known reinforcement learning packages, also some collision of physics going on there, and aerodynamic effects are modeled a lot better than some other packages. So pretty much, some advantages of this is that you can input the thrust vector that you want, and it'll compute the RPMs of the motors that you require. So just to give you an idea of pretty much how this was running. So, we create our environment, and then for each of our 10 gates, we basically use our DDPG model to predict our optimal next action, and then just, step forward based on that prediction, just, classic reinforcement learning setup. And then, either when we were done with our runs, or if we'd reached the optimal point that we wanted, then, we just pretty much close it.
What does it mean, DDPG model? What does it stand for?
Deep deterministic policy gradient.
Yeah, deep deterministic policy gradient.
Yeah.
So pretty much, I can talk about it I'll just talk about it here. So basically, what it does is it uses gradient ascent to ascend the value function pretty much, rather than descending like a cost function. Yeah, so as for the results of the project, so just to compare it to some basic pure RL results, this video will play. So this is what it looks like, just pure RL. You can kind of see the drone just does nothing, just kind of falls backwards. Play it again. Okay, there we go. Yeah, so that's what the result looks like. As you can see, it makes its way through the course. And
so how long does it take to solve this problem?
how long did the course take, or how long did the actual computation?
So it knows all information a priori, right?
Yeah.
Okay.
Well,
Yeah, so this is just a rendering of, so basically it trains the model, then it runs it, and this is a rendering of the run. So the run is all numeric, and then
Yeah, I understand. But how long does it take to solve for the policy?
for the first part, for example, solving the model base is the one that takes much time. That took a couple of hours to run in MATLAB. But with that initial policy in Python, it runs in a couple of minutes. It doesn't take that much.
Yeah, and just for like some more visualization purposes. So down here are the inputs, the motor RPMs. And then I guess like some interesting behaviors I want to highlight. So you can kind of see like the Y position is this sinusoidal shape, not just because of the position of the gates. They're in that, sinusoidal shape. And then the Z velocity is pretty constant. It slightly changes in accordance with the motor RPMs changing whenever it's trying to go from one gate to the next. But just kind of an interesting lineup between like these slight dips in Z velocity versus the motor RPMs.
Welcome to the final presentation. Our topic is called Augmented Reality-Based Rehabilitation Training Purpose. I am Haiyun. I'm with Mike and Jingjie. We're going to introduce how we establish this solution through the soft actuators, HoloLens, and the GP training models. So this is what we're trying to do because we don't have a real patient here. So we're going to replace the human's body by a human dummy arm, which looks like this on a bottom right. And we're going to use two sets of soft actuators, but in practice we only use this one. But we are technically able to further improve it by using both. And we're going to use a HoloLens as well.
So this is just a basic overview of how the HoloLens would work with the soft pneumatic actuator system and how the soft pneumatic actuator system communicates with the local PC, which gets the data from the HoloLens. So we first use the HoloLens to set the point for the dummy arm to point to. So once the HoloLens app is opened up, the HoloLens will start at the origin point of 0, 0, 0, and the red dot will start at the origin point of 0, 0, 1, a coordinate spot of 0, 0, 1. And what we do here is we try and get the angle calculation between the HoloLens and the target point. And we do this by calculating the difference between the Y coordinates, between the origin and the target point, and the Z difference of the origin and target point, as displayed on the figure. And after that, we get the angle by taking the arctan of the difference of Y over the difference of Z. And that angle is then saved onto the HoloLens, and it's retrieved from the PC through a USB connection. And the MyRio microcontroller that is implemented with the soft pneumatic actuator, it gets that angle data from the PC and then provides the pressure to achieve that bending angle for the dummy arm.
So this is the setting of the pneumatic actuator and the dummy arm. So the bending angle of the soft actuator is measured by these two IMU sets. The difference angle will be inputted into the system and as a real-time bending angles and compared with reference angle. Let's having a look at this video to see how it looks like in practice. So yeah, as you can see, these two actuators can realize mostly the most of the range of the motion of the dummy arm. Yep. So let's head into another slide. So here we're going to talk about data acquisition. As you can see on the left side, we use two sets of actuators. They are serving for shoulders and elbows separately.
Okay, so based on the data that Haiyun just collected from the hardware, so we're able to build this actuator, like pneumatic actuator dynamics GP, which takes the current angle and the pressure input at the current moment as input, and then output, and which basically estimates the angle at the next time step. And the training data is going to be the data that just is showing, but we have a problem is that if we want to run it in real time, so we cannot include all of the data because we're gonna compute an inversion of matrix in real time, which is quite computationally expensive. So we did a little bit of tuning for that as well. And then in the GP, what we choose here as a kernel is exponentially quadratic kernel, which is having two hyperparameters included as shown in the equation. And then what we trying to do is to online update the training set that's just shown. So all the training data shown is actually taken under the condition that with this specific dummy arm. But say if we switch the dummy arm to some other arms with different weights, then the current GP model is not going to work in that case. So in order to adapt to the new model or adapt to be more general, in different models, then we need to do this online updating. And so about the number of points included in GP, which is hyperparameter tuning I just mentioned, which we actually had say 50 data points collected, and then we tried different, say 50, 40, 30, and then we find doing 20 points is real time feasible to do the inversion.
and within one loop. And then it's also very accurate in the estimation of the angle. And the second one is that the kernel hyperparameters, which is the sigma and the length. So since our data inputs is angle and the pressure, which is roughly say like 0. So the pressure is from 0 to 60 kPa, and the angle is like roughly in degree, which is like negative 20 to say 60. So we're gonna tune basically the length to match that magnitude, so that we can have a good estimation of the kernel. And then for the optimal control, we grid the 0 to 60 kPa pressure using based on certain interval, and then estimate all of them simultaneously, and then take the closest to one, and apply it in as a part of the optimal the control input we're gonna apply. And aside from that, we also have an extra term, which is a proportional control based on the error that we have at the current moment. Basically, it's just a proportional control, which is k times the theta reference minus the theta measurement. And then the next video is based on the second condition, which is that we take out the tip of the dummy arm. Basically, we are reducing the weight of the dummy arm in this case. So now the GP that we train is supposed to be having some discrepancy with the actual dummy arm that we have. So right now, if we turn on the control, you can see we have a quite large overshoot. That's because the weight is like reduced. So we're still applying the same pressure as we desired in the previous model. So it will have a lot of overshoot. And since we have the proportional gain controller, so it's trying to get back to get to the reference angle that we set, but it's not doing a quite good job. So right now we turn we are online updating the data, and then now we turn off the switch and then re-turn on the control again, starting from the initial condition. So right now our training data of the GP is already replaced using the updated data. Now we can see we still have a little bit overshoot, but then immediately we can get to the target angle that we desire, so which is showing a better performance compared to the previous trial.